Hi, I'm Sean Carpenter from Sonnet Software. I'd like to talk to you about using port tuning techniques for the optimization or tuning of MMIC passive circuits. And we're of course going to use underlying EM simulation to include composite layout effects. Well, first we're going to talk a little bit about what EM port tuning is all about and set it up as a faster way, a much faster way, and a much more efficient way for optimizing MMIC circuits. Now, we have to start with the introduction of some basic tools that one uses for EM port tuning, and so we'll talk about the techniques that we have in our port tuning tool bag. We'll also do a little hands-on demonstration where we're going to add EM tuning ports to an MMIC matching circuit, and then we're going to take that matching circuit with tuning ports into a popular circuit design platform and show you how port tuning and optimization works. So the idea behind port tuning is a little like this. We start with the synthesis of the layout of a particular matching circuit. You can see one pictured here on the left, and then we're going to put a number of internal ports, usually one per component, scattered throughout the electromagnetic realization of this matching circuit. We'll run the EM simulation. We'll take the S parameter data, the multi-port S parameters from the EM analysis, and pull them into a network theory analysis tool and combine it then with some tuning elements. And of course the power here is that we're taking advantage of the very accurate simulation yielded by EM analysis to capture both the layout coupling effects and also parasitics that arise from the actual process modeling. So here you can see we take the EM simulation project S parameters here from this box in the middle and then apply a number of ideal tuning elements which will be attached to those special ports from the EM simulation, and then we can leverage the very fast optimization or tuning capability that's provided in network analysis and combine it with the power of the accuracy of EM simulation. You usually go through a loop where you simulate an EM, add the tuning elements, optimize the tuning elements, then go back and adjust your layout and repeat the exercise, and you do that as many times as needed. The good news is that you only need to do that 3 or quite often less than 3 times total. So let's talk about the port tuning tool bag. What are the things that we need in order to accomplish EM port tuning? Port tuning uses internal solver ports from the EM simulator, and we have 3 types available to us that we'll talk about for the Sonnet suites. One is a series port, another is a shunt port, which is usually realized in the form of what we call a via port, and co-calibrated ports. Usually you only need to have one of these tuning ports inserted per component element in the circuit, and I'll show you what that means. Let's talk first about series ports. Imagine a hypothetical exercise here where we start with a simple transmission line in an EM simulator. We want to tune the length of this transmission line, so what we do is we take our little ideal X-Acto knife, we slice that transmission line through the middle and add a tuning port in the middle. So that's basically a series port now that we've introduced into the transmission line in the EM simulator. Now, we analyze this structure in the electromagnetic simulator. We've got 2 I/O ports and we've got 1 port in the middle. We take the resulting 3-port S parameter data and we load it into a circuit analysis program. Now, what happens when you assign ground, or in your circuit theory simulator attach node 3 to ground? Well, it turns out that you're not shorting it to a global ground, you're actually shorting port 3 to its local ground, or its own reference ground. Well, port 3 is placed between these 2 polygons, positive terminal on one side and the negative on the other, so attaching that element to ground in the circuit simulator essentially just creates a short circuit across the line, and it looks as though it's just a continuous piece of transmission line. Well, knowing this and leveraging this information, we can now create an opportunity to tune this line. So what we could do instead of shorting it to ground would be to place a small inductor across the gap, and doing that can be realized by just simply assigning an inductor in the circuit theory analysis model between the port and its ground. And now we can use the circuit theory optimizer to tune the inductor until we meet the requirement that we have on this transmission line. Runs very, very fast, and it does not use EM at every turn in the optimization loop. So, in a practical application, we can apply this to a spiral inductor, as you see here, and the series port can be placed in one of the turns of the inductor to provide an in situ tuning access, or a tuning port location for tuning a shortened section of inductive line. Well, that works for series ports. How about an analog for shunt ports? Well, in electromagnetic simulators, especially for planar EM simulators, shunt vias or shunt ports provide a means to adding tuning capacitance. Now, keep in mind that capacitances increase and decrease in parallel, so we need a port that can have its reference placed between plates. So one side of the port goes to one plate and the other side to the other. Now, via ports can be placed between the plates of your capacitors for tuning, but you've got to remember that these are not calibrated ports, so that if they become rather long, they can either cross-couple to other parts of the electromagnetic layout, or can cross-couple to the capacitor plate itself, or if they're too thick, can actually reduce the effective capacitance that you see for that capacitor. Well, here you can see a via port that's been attached in a three-port structure for a multi-layer capacitor. Port 1 is the input of the capacitor, port 2 is the output of the capacitor, and port 3 is actually formed by the via port and is across the via and forms for us a location where we can add or subtract capacitances. So now again, we can load the resulting three-port structure or data into our circuit theory tool, add an inductor at port 3 to ground, and now we have a tuning capacitor with which we could add or subtract capacitances to the overall structure. Now, one other type of port that I'll talk about, but we won't actually use in this example, this is very powerful for MMIC and RFIC design, is the co-calibrated ports. Sonnet has the ability to set up multiple closely spaced internal ports and completely de-embed the cross-coupling between the ports themselves, but leaving the cross-coupling between the circuit entities on either side of the port, which is exactly what we want. This is useful when we want to yank the active device out of the middle, but yet leave everything else on both sides of the active device to be able to assess cross-coupling between input and output matching circuits and so forth. Okay, we're going to apply what we're learning here about EM port tuning to an actual example of an MMIC matching network. For this example, we're going to match a 50 ohm input to a 6 ohm output. It's actually going to match into the gate of a high power active device, and we're going to use a two-section matching circuit. It's a low pass, high pass type of matching. A realization of this matching circuit might look as follows. You can see a 3D view here at the bottom, the planar view over at right, and the stack up of the materials here. You can see pictured here at the top. We're going to use 100 microns of gallium arsenide. Then between the plates of our MIM capacitor, we have 0.17 micron thickness nitride material. And then there's a passivation layer of about 3 microns of BCB material over the top. Now, L1 is our shunt inductor to ground. Here's our via in this process. C1 is the series capacitor to the shunt capacitor C2 to ground. It's a via there. And then a series inductor which would go into the active device here that you can see over here at the right. So that's where we'll attach our naming convention to the parts. Now, in each of these structures, we're going to introduce tuning ports, and that'll be the first step of the demonstration. Input port and output port 1 and 2. The series tuning ports will be ports 3 and 6, and our shunt tuning ports, which are going to be between the plates of our capacitors, ports 4 and 5. So let's take a look at it and pull it up in the Sonnet tool. I will load the project into the Sonnet project editor. And here you can see our the top view of our matching circuit. I'll go down to level 1, which will be the top layer of the metallization for the capacitors, and down one more to level 2, which is where our metal for the spirals is located, as well as the bottom plates for the spiral inductors. First thing I'm going to do is I'm going to create port 3, which will be a series port on this inductor L1. So let me zoom in here on an area on the left side of this. I've got a nice little tool up here under Edit, Divide Polygons. We go into that mode and the cursor changes to our little X-Acto knife, and I just draw a line right across with the X-Acto knife to create a split now between the two sides of this turn. Now I can easily put a port on that location by going to my toolbox and selecting Add Port, and the cursor is in the Add Port mode. I click on that segment that divides those two pieces, and right there I have a series port, port 3. Now let's put in a shunt port for the capacitor. Now that's a little bit different. That actually involves first creating a via in the middle of this capacitor, and then assigning that via to becoming actually a via port, which would sort of like the process of splitting the via and putting a port between them to drive between the two. So the first step is to create a via. I want the via to go upward, and so this little tool here will let us create a via that goes up, and then I'm going to create an arbitrary via rectangle. So I'll click into that now to enter the create via mode, and I'm just going to create really the smallest via I can, a really small one right there, and those little triangles there now tell me that the via goes up from this layer. Now you can see it's quite small. I turn this into a port now by going to the add port mode again and clicking on the right in the middle of this via, and that now effectively turns this into a via port. So our port is driving across the via one side to the other. If we take a quick look at the 3D view, you kind of see this if I take the Z expansion and push it, let's even go to something really significant here, really push things up. But now you can see if I tip it around, you can see that little via that's in there with the port number down there signifying that we have a port at that location. And I'll return my Z scale back to 1 again. Now we'll repeat this exercise again for the other capacitor. Go to some location in the middle, add a via rectangle, zoom in again on that, and put a port on top of it. And there's our port number. That perhaps is a little larger than I'd meant to make that via, so I'll just slide it back a little bit and make it a little bit smaller. Okay, and then what's left now, of course, is one more port here on this side, a series port on the side of this inductor. So I go to Edit, Divide Polygons, slice it, and attach a port to the interface between the two. And now you can see we've got 4 tuning ports now that we can use for tuning. So now what we will do is we will simulate this structure in the EM simulator, develop a 6-port S-parameter data block, and import that into a circuit theory or network analysis tool. In this case, we'll use the AWR Microwave Office software. So I'll show you that in just a second. And here we have a fresh blank AWR session, which will open up a new project. And I'll show you it's really quick to bring in this project where we've already created and simulated with our EM ports already into AWR simply by creating a new empty project in AWR. We'll call it Iter1 EM ports, and we'll select Sonnet as the simulator for this structure. I will create. And it gives us a blank project now into which we can basically push the completed Sonnet project. So I go back to this EM structure, I right click on it, I open it in the native editor, which will be the Sonnet simulation client, and up comes Sonnet's XGEOM or Sonnet project editor, and we need to load that project that we had just worked on. We need to load its contents into this one, and so when our project editor is called by AWR, an MW Office menu is created, and we'll load Sonnet project, and it warns us that we're going to be replacing what's in this, of course, empty project, and we'll locate our Iter1 project right there. And you can see here, this is the project that we just worked on. Okay, and if I save it and I close the project, the project editor goes away and Microwave Office comes back up telling me that I have an option of using the native editor for future edits to this project. It doesn't really matter one way or another, but I'll select yes. And now you can see our project has been, this EM project in AWR now has been populated with this Sonnet project that we just created. Now the simulation data also comes with it, and if we go to the elements and go to the subcircuits, you can see here is our S parameter block, which now we can build into a schematic and go on to the next step. Well, we've done a little bit more work on our Microwave Office project now. We've put in the ideal circuit, which of course was the first initial synthesis of the matching circuit that would be required to match 50 ohms to 6 ohms. And also we have another circuit here which uses an EM simulation of the original realization but without tuning ports, and that project looks like this. You can see there are no intermediate or internal tuning ports in this version, and so then we can compare then the ideal circuit response to at least the first layout, and of course as we saw before, we're off just a little bit. Now coming back to our tuning circuit, I have here my first iteration tuning circuit, and you can see my tuning elements have variables that control their values, and here's my block of parameters that control that. Now it's interesting to be able to take, and I'll bring up a plot now that shows us the ideal circuit response. We'll ignore that for the second here, but I have two versions of input and output reflection coefficients plotted. One's the version of the circuit without any tuning elements, and the other one is a version that uses zero-valued tuning elements. And this is an important one to look at because it tells us whether the presence of those tuning ports is interfering to an appreciable extent with the response of the circuit. In other words, are those tuning ports getting in the way, and will they render this particular process invalid? Well, we could see very, very small differences here, so I think this process or this approach to tuning and optimizing the circuit should work well. Now we can work with tuning a bit here, and in AWR we have these nice sliders. You can also find that in ADS. And what I have here are the values of those ideal tuning elements tied to slider values. So here I can vary C1, for instance, and add or subtract capacitance to that first capacitor in the circuit. Here's C2, the second one, the shunt capacitor, the series capacitor. That changes, and we can see how sensitive the circuit is. Here's adding or subtracting inductance for the first inductor and for the output inductor. That gives us some insight into how the circuit responds and how sensitive it is to each of the values of the internal components. Okay, well, we've established a circuit here now that we can work on and perform some optimization on as well as tuning. So what we're going to do is set up some tuning goals. We want to set this thing so that we drive the input and output reflection coefficients to be as broad as possible in the sense of bandwidth, but still achieve a 15 dB match or better, and the through loss should be no more than 1 dB. So when we run the optimization, and the variables really are just the values of these tuning elements, the capacitors and inductors, and we wind up with these values for the tuning elements. We need to increase L1 and L2 by 0.4 and 0.13 nanohenries respectively. C1 would need to be increased by about 0.4 puff, but we could decrease C2 by about 1 full picofarad. So a fair amount of change in tuning elements, but again, remember, we're splitting the poles so we can achieve a wider band, and so that you can see here in this response now of the optimized circuit, and this is what we've achieved. Now, just to compare the original layout to our first pass modified EM layout, you can see clearly we've increased the bandwidth, and the match has degraded a little bit in band, but still perhaps acceptable for the application we're working with. Now, to get to that second iteration, what we could do is go back to the EM circuit that had, or the EM layout that had the tuning ports, and adjust our elements. Now, I chose my degrees of freedom to be a stretching of the inductors in the lateral direction, left and right, and also a stretching or shrinking of the capacitors in the vertical direction. So that's how I changed the values of my components. As a designer, you have intuition about how much change would affect a certain amount of shift in the values of these components, or you could create a parameterized Sonnet project of each one of those structures and sweep those values in order to create a family of curves so that you could see how much inductance is increased when you shift the lines. Let's say stretch the inductor by 10 microns or 20 microns. Now we repeat this process now with the new version of that EM circuit and run the optimization again with the goals that we have. And here now you can see on the second iteration the changes are much, much less, except the value of C2 did need to be shifted down again another quarter of a picofarad. But you get a sense for how this process works in the optimization loop. Now remember, at each turn of this optimization process, we're doing all the heavy lifting of optimization inside of the network theory domain where it's very, very fast, and only using electromagnetic simulation once with the tuning ports installed, which makes this process much, much faster than trying to use electromagnetic simulation at every turn. Well, to be complete, I just wanted to show you the iteration changes for each of the tuning elements from pass to pass. And you can see here that as we get down to iteration 2, there's very small changes required for the various tuning elements in order to achieve a progressively improved response. It really was essentially complete. You could say after 2 passes, you probably could say it was essentially complete after 1 pass. And of course, all the optimization was done with the circuit theory netlist simulator, which is where things happen really, really fast. That's probably the most efficient way to do something like this. Here in these plots, you can see how the progression has gone with the input and output response as we've gone from iteration pass to iteration pass. You can see pretty clearly in these graphs that we reached pretty close to the ideal response even after the first optimization turn. Here's a look at the initial layout. So here you could see our first iteration, and on the right you can see the final layout, which achieved a very nice wideband match and achieved our objectives of shifting the match back down, centered around 3 gigahertz. EM port tuning is a powerful technique, as we've seen, for tuning and optimizing MMIC matching circuits and a variety of other circuits. It uses underlying EM analysis, which is highly accurate, but it leverages circuit optimization, which is very, very fast. So we're using the strengths of both approaches. The EM electromagnetic simulation for accuracy, the circuit theory optimization for speed is a lot faster than having electromagnetics involved in every turn of the optimization loop, and it has the added benefit that the designer, you, are learning a lot more about your circuit. Thanks very much for watching this presentation. If you have any questions, please contact us on the web at www.sonnetsoftware.com.